All right, I'll go ahead and get started. First of all, welcome everybody. Thanks for attending. I'm sure we'll have a few more people coming on as we get started, and many people will be watching this afterwards. But welcome everybody to the Edge Computing, a feasible and integrated approach to collecting systems data. And we have a wonderful PhD candidate that's going to present for us that Dr. Barger will introduce in a couple of slides. So FLATE, there's an entire FLATE team, and which I'll introduce in a minute, but FLATE's vision is to drive Florida's world-class manufacturing workforce education and training. We've got a great team. The FLATE team is kind of spread throughout Florida, but I'm the executive director. We've got Dr. Marilyn Barger, who's the senior education advisor with us today. Teresa Potter, who's on the call, is our manager of community engagement, and Daniele, who is the career and technical education manager. She is traveling today and can't be with us. But great team, been doing a lot of great work, and we're here to help you guys, and I'll show you a few ways that we do that. One of the ways that we do that is through curriculum reform and development, student pipeline development, and professional development for educators. Yeah, thanks for doing the slides, Teresa. For some reason, the buttons are hiding from me. One of the ways that we help with student pipeline development is we promote manufacturing education. We do a lot of manufacturing, helping coordinate a lot of manufacturing day, month student events. We've got a great manufacturing dashboard. We host manufacturing educator awards. We publish monthly newsletters, support. We also provide support for STEM summer camps and develop and disseminate resources for recruiting girls. For the professional development for educators, we've got, if you haven't attended, please put it on your calendars. We've got one coming up. The next one's coming up the end of September, but it's the Forum for Engineering Technology Education, or what we call the ET Forum. This year, it's going to be in Palm Beach State College. We also do technology demonstration projects, educator workshops. We help conference attendance support for faculty, a webinar, which you're attending today, and program mentoring. So we can help schools across Florida develop new programs, work with industry and other educators. So we've got some wonderful resources. FLATE's been around for about 20 years, and it's great resources. The FLATE.org website is to your left. And then we've got Made in Florida in the middle, and a wiki to the right. On that, the one on the left on the FLATE.org website, there's some really good resources, one of which is a new dashboard that was just been updated, and it's got lots of great resources about manufacturing in Florida. So please, when you have a few minutes, please go check out the websites. If you haven't been there in a while, check them out. There's some great resources there. And many of you have found out about this webinar by going to the FLATE.org website, or you may have heard about it in the newsletter. But any past events or future events, you can find on the FLATE.org website on the far right-hand side. Now, it's my honor to hand it over to Dr. Marilyn Barger, who's going to talk with you about a grant she's leading and introduce our speaker.
Hi, everyone. Good afternoon. Just a quick update for some background and to give NSF some acknowledgement for funding the work that's going on that Purvee's going to show us or share with us in a few minutes. Right now, we're working on an active grant from NSF ATE, and we have 6 goals, but it boils down to activities in 3 areas. So I'm just going to kind of give you an overview of that. We are working on new programs, new degree programs, or parts of degrees or specializations in Florida. And we've done a lot of background work with checking with industry and surveying them and talking to them, as well as faculty around the state, and are in the process right now of finalizing this ASET, Engineering Technology, with a specialization in advanced automation. So it'll be a little different than advanced manufacturing. and focus on all those communication and networking. We'll add in those skills in those areas, cybersecurity, et cetera, kind of the digital aspect of advanced manufacturing today. And also other industries as well, very appropriate for a lot of other industry sectors. And along with that, we're also working on a bachelor's degree. We have a BS Engineering Technology in the state that our programs align with very closely. And a new 4-year option will be available in the coming months. We've been working on with this project called Industrial Engineering Technology. And that's, again, with our work with our industry partners and educators around the state, and working hard to make this as seamless a 2+2 transition for the AS students as possible. These programs that they're held at Daytona State primarily, and they are offered online. So students from any of the 20 colleges around the state that actually have the ASET degree right now articulate into the BSET, one of the flavors that they offer. And it's a great opportunity for our students to keep learning. So we really work hard to keep that alignment of those two programs, the AS and to the BS, intact and easy for the students. Our work with engaging industry has really focused around 2 big activities. One is to establish a statewide industry advisory board, which we've done. It's now about, gosh, I don't know, a year old, a year and a couple months old. And what we did since we have 20 colleges around the state that offer this degree, we have invited the colleges to recruit someone from their own industry boards to the statewide board. And the state board actually has the same opportunities and the same role as the local board. But we are hoping that it will give better networking opportunities for the students and the industry around the ET degree, better understanding of the skill sets that the graduates have, as well as their oversight of what we're doing, helping us understand what their needs are across the state, since we have a statewide curriculum, and it has to meet everybody's needs at some point. Sometimes that's easy, sometimes it's not so easy. So we're pretty excited. We now have representatives from about half of the colleges that offer the ET degree on the board, and are looking forward to growing that a little bit more so we can include everybody in all areas of the state. And another is just interviewing industry, different companies for their perceived needs, what they think is coming in their own companies for Industry 4.0 and the next implementation of technology. And lastly, we for the grant, we're providing professional development for the educators. And this is focused on some of the new skills that will be in these degree programs, including what we're talking about today. We started thinking about using concepts of edge computing, since we're often working on the factory floor, and a lot of that factory data is not really data that needs to go to the cloud. Sometimes it needs to be used within the factory floor and parsed out for some of it going into the cloud and company databases. But using that as an opportunity to introduce some of the aspects of Industry 4.0 in the technology area, but also more specifically in the data area. So we got a lot of comments from industry saying that students really needed to know how to work with data, understand good data and bad data, and recognize good data and bad data, and then be able to visualize it. So in the context of edge computing, we've gone down this path to use it as a tool to collect data from various processes in a factory, and bringing them together and taking a look at what they have to say. And so as part of that, we engaged with some really smart people at the University of South Florida, right here next to us in Tampa, or next to me in Tampa, also my alma mater. So to help us from the mechanical engineering department at USF, to help us understand how to do this and to develop some prototypes for us that we can use in an educational setting for our educators and then likewise for their students. So what you're going to hear today is Purvee. Purvee, I don't know how to pronounce your last name. I just realized that, so I'll let you do that. She's been working along with a previous PhD candidate. Well, I guess he's still a candidate. He's just not working on this project. Donald McClarity, who started with us and has passed it on to Purvee to help us develop a affordable setup that demonstrates edge computing and then also gives us an opportunity to work with some data. So I'll turn it over to you using the Raspberry Pi system. Purvee, you ready?
Thank you so much, Dr. Bhatia. My name is Purvee Bhatia, and I am a PhD candidate at the University of South Florida. My research focuses on smart manufacturing along with integration of artificial intelligence. And I've had the wonderful opportunity to work under the guidance of Dr. Bhatia to assess using affordable devices as our edge computing devices. And today I'll be talking about that. Thank you so much. There seems to be some issue with the controls. So a general overview of what is to follow for the next couple of minutes. We'll start with our basics on edge computing, what's the need for it today, and we'll translate that into the setup that we have assessed, which is environmental monitoring with sensors along with edge computing. We look at a few sensor technologies, how we selected the sensors and the measurement methods, followed by the hardware and software integration that we used to collaborate the sensors with the Raspberry Pi, and our learning outcomes and the future work, which would involve integration of edge computing devices with artificial intelligence. So first we'll go with the overview of environmental monitoring and edge computing. Next slide, please. So over time, sensors have been used to monitor and control different aspects of different processes. And these days, we are able to identify areas that use sensors a lot. A lot of processes have been made more efficient by the use of sensors. And with increasing pollution and with increasing environmental degradation concerns, we have included using sensors or sensing technology to figure out the environmental and the volatile organic compounds that are present around us. These advanced technologies essentially provide us with powerful and indispensable tools that enable us to analyze and address any concerns that we have. Monitoring and collecting data through our environmental sensors helps us in determining the environmental parameters and allow us for real-time data collection, which can enable informed decision-making, improve public health, and safeguard our ecosystems. Next slide, please. So in the aspect of edge computing, we have combined using environmental sensors along with edge computing devices to form a feasible and affordable platform for data collection and processing. Before we jump into the nitty-gritties of how we propose this entire framework, I'll just give a basic overview of what edge computing is. So essentially, traditionally, data is generally transferred from our devices onto a central data center for processing. But over time, as we collect more and more data and the unprecedented amount of data that we've been collecting, we need to have more network capabilities that allow us to improve application performance. And this is where edge computing comes in, where we process information closer to the devices and closer to the users who consume it, as opposed to moving it to a central data center. Now, it's becoming more and more popular over time because enterprises need to collect and analyze their raw data more efficiently and to make informed decisions, to increase their operational efficiency and overall business operations. A few advantages that edge computing offers us is, as listed in this table, which is reduced latency. So with high demands of data transfer, there's less latency when it comes to data translation. Then we security, so a majority of data is processed and secured locally, it's stored locally. So what happens is there's improved data security. It doesn't need to be encrypted to send to a central data center. Increased productivity. So by analyzing the data at the source, organization can improve their facilities. They can improve the areas where they're underperforming. And essentially, we can team this up with artificial intelligence and machine learning moving forward to give insights as to how the processes look like. We also have reliable performance in terms of edge computing because we significantly reduce our chances of operational downtime because of network or connectivity issues as we are processing our data closer to the devices. There are many industries that are already utilizing edge computing. So we have manufacturing industry where computing solution essentially provide automation. They enable collection of data on site along with improved production efficiency and rapid machine-to-machine communication. We also have industries in autonomous vehicles that basically use the Internet of Things or IoT sensors to collect the data, and then they require real-time data processing so that they make rapid decisions. Along with energy as well as healthcare, where data again is stored near, for example, maybe turbines or solar farms, which gives us a better outline into the data pipelines and informed decisions. Next slide, please. So the key objectives that rise from these two factors that we have focused on in this project is deployment of edge computing using Raspberry Pi. We want to leverage a single board computer, an affordable single board computer, which could collect data from a host of sensors and then perform a number of data analytics technique and analyze data right at the edge. And our goal is to enable the measurement of environmental parameters. That way we can have a responsive system for our smart environmental monitoring, which we have developed as a case study to show the capabilities of Raspberry Pi as an edge computing device. Next slide, please. So Raspberry Pi, the few advantages that Raspberry Pi offers us is it's a very powerful tool which can help us with a range of connectivity options. It is very versatile, it is expandable, it does not consume a lot of power, and it's very compact, which allows us to put it anywhere in our processes for data collection, and it's fairly easy to work with. Next slide, please. So now that we've talked about our edge computing device, we're talking about the sensor that we utilized in this case study to assess the capabilities of Raspberry Pi as an edge computing device. Next slide, please. As I had mentioned, the case study focused on environmental monitoring and a smart environmental monitoring setup. So we use low-cost air pollution sensors to report and detect different air pollutants, particulate matter, carbon dioxide, and other factors like temperature and humidity. And depending on what kind of sensors we use, we can obviously collect data on various environmental parameters. In our case, we have selected 4, which I'll be talking about further down in the presentation. We are going to be looking at temperature, humidity, our volatile organic compounds, as well as our carbon dioxide. Next slide, please. So in the selection of sensors, so how once we have our device set up, which is our Raspberry Pi, how do we select the kind of sensors that we want? There are a host of air quality sensors available in market, but the goal was to have something which is easily plug and playable and does not require intensive calibration. We wanted to look at the power requirements, the types of sensors, the range and the sensitivity, because some sensors need to be calibrated very effectively in their known substances for them to perform very well. So we looked at calibration procedures, something that can be done very easily. We looked at interfacing options. So what can they interface with? Would it just be Raspberry Pi or multiple other microcontrollers or single board computers as well? So these were a few key things that went into selection of sensors for our environmental monitoring setup. Next slide, please. So these are the 4 major components components that we'll be utilizing in our case study, we used, as I mentioned, we used two sensors. We used Adafruit HTU3i and SGP30 air quality sensor. We combined that with our Raspberry Pi, and we used essentially a hat to make sure that our sensors and our Raspberry Pi communicate well with each other. Next slide, please. So I'll talk about the proposed framework and what that looked like. So essentially, we combine the sensors, the sensing capabilities with multiple sensor complexity. It can be a single sensor, it can be multiple sensors. We combine that with our edge device, which was our single board computer, and we performed advanced data analysis and visualization techniques to see how what kind of data are we collecting, what patterns, anomalies, and trends lie within the data, and future work will also reflect upon AI integration. Next slide, please. So we also utilized, so the goal was to make it a very plug and playable option. I wanted to eliminate the usage of breadboards and jumper wires initially for data collection, something which we can just plug in and play and start collecting data, because the focus wanted to be data collection and seamless data acquisition. So what we did was we utilized the I2C protocol, which essentially enhances data transmission. So we had the STEMMA QT connectors, as you see on the screen. We connected it to a multiplexer, so that way we can have multiple sensors on that same channel, on different channels in one single device. So we don't have to connect multiple Raspberry Pis as well. So we utilize that, and we use the STEMMA QT ecosystem, so that we have a very adaptable platform and we can plug and play our sensors and start collecting data right away. Next slide, please. So now we'll talk about how we integrated these hardware components into two different case studies. So the first is our environmental monitoring station. In this setup, what we essentially did was we wanted to measure various environmental parameters, and we wanted to look at how they affect our overall real-time data analysis. We wanted to look at what sort of trends are there in the data. So if you could click again, there's a couple of animation in here. Once more, please. So this was our hat that we used with the Raspberry Pi. Another, please. Yes, as I mentioned, the breakout channel, so we could connect two different sensors on two different channels, and we can just put them in different locations or maybe the same location. Another, please. So these were the sensors that we were using. One was the temperature and humidity sensor. The other one was the air quality sensor. And so how this data gets collected is, as Raspberry Pi works in a Linux environment, the first set of data that gets collected, if you could please click again, is something like this, which is not really readable. It is readable, but it's not really analyzable. So this is the raw data that comes to us on the Linux environment that we have. So our goal was to translate that into a more readable format on which we can perform different data analysis techniques. So what we did was we wrote a Python code such that the data that we see over here essentially gets translated to an Excel file, and then we can perform using Python, we can perform all sorts of analysis on that data and see the results that we have. Next slide, please. So the few data analytics technique that we employed were descriptive studies. So the data that we collected, we found out the mean, median, and mode. For all of the data, we looked at the range, the variance, as well as our standard deviation. We also looked at how much data lied in the first quartile, for example, the value under which 25% of the data lies, then median data, and then 75%. So we wanted to see what sort of data lies in what categories. And these were the initial descriptive studies that give us an idea as to how the data is spread out across the time that we had selected. Now, this data was collected while we were performing 3D printing. So essentially, it looked at the emissions that were coming out of the 3D printer. It can be translated to any other case study that we have, since the sensors we can easily put them in a different environment that we want to measure in. But yeah, so we looked at the range that was given to us. So we know that the humidity showed a bit more variation and had a wider range. The temperature was pretty stable with slight deviation, and our CO2 levels showed variability with a standard deviation of 4.46. So this was the initial descriptive studies, followed by, next slide, please. We did time series analysis as well. We wanted to see the trends that data show over this time period, any patterns that we can identify, any fluctuations that occurred, if there are any unexpected spikes, why were they, what were the reason behind them, which gives us insights as to what process was happening during that specific time, which led to these spikes, or what trends. So we plotted some time series and graphs as well. And we basically found out that the CO2 levels do fluctuate a lot. They range from 413 ppm to 435 ppm, and there are frequent peaks and valleys, as opposed to our temperature, which does not show that much variability. So we can see what sort of operation was occurring right in that time to assess what was affecting our environmental parameters. Again, the good thing about this entire setup is it can be placed into any case study, and we can analyze the data directly from that specific case study. And these were the plots that showed us the general trends, the patterns. The anomaly that we observed was in our volatile organic compound gas concentration and our variability in carbon dioxide levels, which again, we can investigate why that had happened, so this data gives us a lot of insight into the entire process. We also did heat map analysis. If you could go to the next slide. So we performed correlation analysis to explore the relationship between different environmental variables. For example, how maybe temperature affects humidity, humidity affects the gas, and so on and so forth. So the image that you see over here is a heat map that represents the correlation matrix for all of the environmental variables in our data set. And to give you some context, so the values range from -1 to 1, where 1 is a perfect positive correlation, -1 is a perfect negative correlation, and 0 shows no correlation as well. The color gradient is also designed like that, the color ranges from blue have negative correlation to red, which shows positive correlation, and darker colors shows higher correlation. So the most correlation that we found was between temperature and humidity. There was a strong correlation there, and there was strong negative correlation actually, and we had a very weak positive correlation between the temperature and CO2 levels as well. So this gives us more insight as to how one parameter affects the other. The diagonal elements that you see, the ones that are all along the diagonal, are perfectly correlated onto itself, which is why the map looks like that. But this helps us quickly visualize the relationships between different variables. Next slide, please. So apart from the time series plots, we also did some box plots, as well as some the histograms. So the box plot essentially again showed us the central tendency and the variability, as well as the outliers that were in the data. So right off the bat, it gives us visualization into the data that we had collected. The histograms on the left-hand side, which you had collected, show us the distribution of the entire concentration of gas as well as temperature over that time. So the frequency distribution for each variable is shown through the histogram, which helps us identify any unusual patterns, how the data is spread out. So these were a few data analysis techniques that we applied using Python to understand how the data looks when using Raspberry Pi as an edge computing device along with the sensors. Next slide, please. So these are just example of the code that we had used. It's pretty simple. Next slide, please. Another experiment that we wanted to run was to have an enhanced setup which allows for environmental monitoring with threshold based results. So we wanted user interaction with the device as well. So this was a more traditional setup with our breadboards and our LCD screen. So where the user can interact with the LCD screen using a joystick, and the Raspberry Pi reads data from two devices. Over here we have a sensor as well as a thermistor, and which provides for robust real-time environmental monitoring and alerts. So what the idea was, if we could go to the next slide. So the idea was that the Raspberry Pi processes data from the thermistor and sensor locally, and it reads the data, checks it against the threshold, and generates alerts without relying on a server. And if there's a temperature goes above certain threshold, we can we can create alerts, or we can also create a complete feedback where we can control the process. In this regard, we can control the 3D printing process using Octoprint. And we also have resource efficiency. So we leverage a low computing device to allow for those real-time decision making. That was the idea behind this enhanced setup. So we could accommodate real-time environmental monitoring and alerts. Next slide, please. So the learning outcomes that we had from these two case studies that were shown over here were, number one, sensor integration. How do we integrate different sensors with the Raspberry Pi? Data processing. We started with the basic data processing techniques all the way. We can move on to the advanced levels, understanding how to use different outputs for real-time alerts and display for data monitoring, and utilizing an affordable device like Raspberry Pi to process all of the information, obviously near the edge, without sending the raw data to the central server. Next slide, please. Our future work in this area, so moving forward, we want to integrate the concept of artificial intelligence, or AI, into our edge computing device. Now, we want to see whether we can integrate these two things along with cloud capabilities to create models that allow for predictive maintenance. So now that we've collected the data, we can utilize that data, and we can definitely have models that tell us at certain ranges maintenance would be required. We can use it for process optimization. So for example, if we take 3D printing in this regard, we can see which printing parameters affected our environmental outputs. That paves way for more sustainable approaches. We can do our tracking of our assets as well. So AI can be included in these examples to provide more insights from the data. So the data that we've collected will form the basis for all of the predictive modeling that we can do. There's another example that we can use. So all of these sensors, since the Adafruit library that we use, they have a host of sensors that we can use all throughout. So energy measurement, we can optimize our processes to make them more energy efficient, make them more sustainable. We can also use them in automation. So using, in this example, I've given an example of smart homes. We can also have smart factories where we control different systems to make sure that any emissions that we have, they're counteracted maybe by certain placements of the HVAC, certain functioning, and all of this data can definitely be processed further, enhanced capabilities with AI. And this is what our future work will touch upon moving forward. Next slide, please. And this was, I would say, a brief overview of using Raspberry Pi as an edge computing device and leveraging different sensors for a plug and play option, as well as a more interactive hands-on option where the user can interact directly with the device, and the future work in this area as well. I would like to thank you all for the time, and if there are any questions, I would be happy to answer them.
So if anyone has any questions or comments, you can certainly either put them in the chat or raise your hand or just start talking. Unmute yourself and just start talking. Thank you, Purvee. That was great. You sure can talk fast, but it was pretty understandable. I think I got all the messages you had to give there. Are there any
I
questions?
have, this is Mehdi Miri from Polk State College, and I had a question. I've always been curious about the scalability of Raspberry Pi. You know, with an I2C serial interface, you know, how do you add I/O boards, and how many I/O? What are the limitations of the I/O boards? And you know, in a manufacturing plant, sensors are widely distributed far away, and usually currently what they do, you use an Ethernet network that has a much longer range, and you will have remote I/O modules that you can put anywhere in the plant and collect the data. Then you log that data into some cloud server, and then other apps that, you know, like AI you mentioned, AI apps will tap into that data and develop models for machine. Usually they use neural network models, which are far too complex, in my opinion, to be able to do with a Raspberry Pi. So I guess my main question is scalability. How do you add I/O modules, and what are the limitations?
So in terms of limitations of Raspberry Pi, the one good thing about the scalability, like you had mentioned, so you had mentioned that obviously we require sensors at different setup inside the manufacturing floor. So the scalability of this is, since it's pretty affordable, we can definitely have different sensors in different areas. Also, in regards of Raspberry Pi, there have been some studies where we can inculcate a small large language model within Raspberry Pi, but the idea would be for it to collect the data and basically use that data in terms of AI for further predictive modeling. It definitely does not have that much memory to store the data in the Raspberry Pi in itself. So there we can definitely utilize the cloud capabilities that we have, so the data directly goes to a cloud server, and that is where it gets analyzed. The scalability option is something which we would also look into in the future. We wanted to first of all assess the capability of Raspberry Pi to even work as an edge computing device. But that's a very good point to look at in the future as well, along with the AI integration, to see whether we can scale it up, use cloud along with AI, and look for more options.
Thank you.
Yeah, I think we were interested in trying to put together something that we could use for teaching in our engineering technology degree that would help students, give us an avenue for talking about some of the Industry 4.0 technologies, but also some hands-on activities they could do with working with the data in a different way from different sources. And combining them and looking at the relationship between data, because that was something the industry had continues to point out to us that they want. So whether or not, you know, how far the scalability is available is not a real important question here. It was something that was affordable and could demonstrate and provide us with real data, instead of having to give the students just some data sets from somewhere, that they could actually generate the data and deal with it and make decisions themselves about, you know, different questions that we might ask them for. So certainly is something to consider going forward, but for large scale implementation. But right now, this is where we are. Anybody else? Questions, comments?
Purvee, I do have a tiny question, just a thought. I'm looking at the plots with the, not the box plots, but the other ones. And I noticed that the scales were different, that for the humidity and the temperature scales. And I was wondering, yeah, you can go back. Okay, yes. So the humidity, I was wondering if there could be shown a relationship between the temperature and humidity, but the humidity doesn't pick up until after the temperature distribution. Was there no correlation prior to that, if that makes sense, when you're looking at the scale? I could be wrong.
So this scale was over time. the
Okay.
data. So I made sure that all of the data was collected. So we did have one issue, which I figured out later and I fixed it, was that when you're collecting data from two different sensors and you're translating all of the data, you're getting huge amounts of data at the same time. So initially we had some latency, so we weren't getting data at the same timestamp, but then we fixed that. And after that, we did not have that issue. Earlier we were getting temperature, humidity, so it was a couple of seconds gap, but then we fixed that, and finally we had the data come up at one single timestamp as well. So right now it's against timestamp, so I think that's why the scale looks different. But if you go back to the previous slide where the correlation was there, over here we had put them on the same
Okay. Good.
scale.
Thank you.
Yeah, but we did understand that when you're translating data from different types of sensors, the amount of sensors that you increase, that issue of latency does occur, which we were able to resolve, fortunately. So moving forward, that should not be an issue either.
Great. Thank you.
Thank you.
Anybody else? Comments or questions?
And what protocol do you use for collecting sensor data? Is that a poll response protocol? Or
I'm
is
sorry,
that
your voice was breaking up. Can you please repeat the question again?
what protocol do you use to collect your sensor data? Do you poll sensors individually and wait for the response?
So we pull sensors. So we pull data every 30 seconds from all sensors simultaneously. So we give one sensor on one channel, second sensor on the second channel, and then we pull data together every 30 seconds. That was what we decided to do.
Okay.
The Linux GUI that you saw, essentially the data was being shown there, but then we translated that to a like an Excel version for better analysis.
Anything else, anyone? We ran through that pretty fast. We might be ready to move forward. So I'll turn this back over to is this you, Teresa?
It can be.
Or Ernie, or I can just do it. So I think Ernie mentioned at the beginning that all of the webinars that we have had, which are listed here, are still available. They were all recorded and edited nicely by Teresa. So cutting out some stuff at the beginning and some stuff at the end. So they're nice and compact on these particular topics. So if you're interested in those, you can see the link there at the bottom. I believe this is the last one this year. I'm not sure if we scheduled the one more that was potentially coming up.
I think this is the last one.
The last one for this year. But I will remind everyone or tell everyone, some of you know, some of you have already signed up, and I think it's full, but you never know, there might be a good chance to be on a waiting list. We are doing a 2-day workshop at Hillsborough Community College in August 8th and 9th, Thursday and Friday, and Purvee will be going through this. Each attendee will be working on their own little Raspberry Pi system to put together the system and also work through some of the data that examples that you saw here, and whatever else comes up over the summer to add to it, and probably in the AI and some opportunities in the using the cloud computing up as well that were mentioned.
Hey, Marilyn. Yeah, thanks,
Yeah.
Mel. If I could just add, certainly I know many of you on this call have contributed to some of these webinars, but if you've got some ideas on some new webinars, or you're doing some new research, or have some interesting labs that you want to share, please reach out to us and we can organize a webinar around the content that you're creating. So if you'd like to share it, let us know. We can turn it into a webinar.
And that would be next year in the fall or the spring, Ernie?
Yeah, we'll have to see probably starting in the fall. Yeah, depending on who's got what and how long it takes to create it. But certainly we could set that up for the fall.
Okay, great. So I'll take advantage of that if you've got something you want to share. It doesn't have to be from a grant. It could be from just work that you're doing in your own classrooms and topics that that you've explored that you think others will be interested in, and et cetera. So that's all we have from our end. So unless anybody has anything else, any other last comments, we can give you guys back 15 minutes.
All right, well, thanks again, everybody, for joining us, and we'll talk to you all soon.
Thank you.